Hello, guys. I hope that you had a great day so far. Today, we are going through a problem with the application of derivatives in calculus, where we find the volume of a box such that we maximize it. So we have Hossein here. He's gonna help me
Hi, everybody.
find a solution. Hello, Hossein. How are you today?
Good, good. How are you?
I'm good, thank you.
Very good.
So let me read the problem for you. We have a 10 centimeter by 10 centimeter sheet of metal, which to be used to make an open top box by cutting 4 squares of equal side x out of each corner. So as you can see in the sketch below, you have a square 10 by 10 metal sheet, and you are gonna cut 4 equal squares of each corner. So when you cut it out, then you can fold each side, to make an open box, as you can see on the right figure. So when you have that open box, we want to maximize the volume of the box by changing x. So yeah, that's correct. You actually named x on the sides of each square, a small square on each corner. So as you can imagine, when we cut the each corner, which is highlighted, blue highlighted, then you can fold through the dashed lines, and then you make the open box on the right side. So for the volume of that open box, we want to maximize it by changing x. So we want to find x to maximize the volume of the open box. So the floor is yours.
Okay. Yeah. This problem is optimizing using derivative. And I see we have a sheet metal with the size of 10 by 10. We're going to cut x. So, and then when we fold it, the resulting is a box like we see on the right side. So if I name the sides as let's call it A, and this side, let me call this B, and then call this side C, then I think if I compare the two figure, A is going to be equal to X after folding.
Yes.
And then B is going to be equal to 10 minus 2x, because we're cutting 2 square from both sides. And then C.
Could you please show B on the left sketch?
Sure. B is this from here to here. Think so.
You can use the laser pointer.
Yeah, with the B is from here to here.
Correct.
Which is 10 minus 2x, and then C is from here to here, and is equal to 10 minus 2x.
Okay, thank you.
And then this A here is this cut. And the volume of the box, if I call it V, is equal to A times B times C, which is equal to X times 10 minus 2x times 10 minus 2x, and I can simplify it to x times 10 minus 2x squared. And because it's an optimization problem, so to optimize the volume, we need to find the maximum of this volume. To find the maximum, the derivative of this function need to be 0. So
Equal to 0, correct.
right, wherever dv with respect to dx equals to 0, then whatever x that satisfies this equation, if we put it into the equation above the volume, then it's going to maximize it. But we also have some constraint here in terms of like for x, those constraints are, I think, constraints. So x need to be greater than 0 because we wanted to make a cut if x is 0, that means that we don't have any cut.
We don't have anything.
Yeah, correct. It's just a flat sheet. And then another constraint is when we make a cut, we just wanted to end it up with a box. We don't want it to cut the whole sheet. So 10
correct
minus 2x, or let me write it like this first. So for the first constraint, in other words, a need to be greater than 0, meaning the box has a height. And then the second constraint is b and c need to be greater than 0. That means
correct
minus 2x need to be greater than 0. Then x, if we rearrange this equation and isolate x, so x need to be, maybe I should write down the steps because that may confuses people. So I subtract 10 from both sides. Then I get negative 2x greater than negative 10. Then if I multiply both sides by negative 1/2, then I'm going to get x, because I multiplied by a negative number, I should flip the inequality sign.
Correct.
So x less than 5 is another constraint. So whatever x that we obtain, it should be between 0 and 5 to make sense.
That's correct. Yeah.
So
that's always good to, for optimization problems, it's always good to construct our constraints,
Right.
And that's a physical problem. We know that, we have those kind of constraints. So thank you for mentioning that, Hossein.
No problem. So I just go ahead and find the derivative of the volume that I wrote on the first line. So dv over dx is equal to, so what I have here is x times 10 minus 2x squared. I can use product rule to find the derivative. Another way is to do the multiplication and find the derivative that way. But I think
finding a polynomial and then
right,
differentiating the polynomial. But this way
I think it's shorter.
Yes, yeah.
Okay.
And you practice the derivatives rule, better.
Okay, I think we have a video on product rule on our channel. So for the viewers
yes,
that they wanted to review that, they can watch that video. We put the link here. So
that's correct. Yeah.
So the derivative of x is 1 times 10 minus 2x squared plus the derivative of the second multiply is 2 times negative 2 times 10 minus 2x.
Yes.
And then if I'm just trying to simplify this equation. So 10 minus 2x squared plus or not plus, maybe minus 4x times 10 minus 2x. Okay, and then
Yeah.
I have
You can factor actually 10
right
minus
dv
2x
over
yeah.
dx 10 minus 2x. So we have it here and here. 10 minus 2x. Then I have 10 minus 2x minus 4x. And then I can simplify this further like this. 10 minus 6x. And then I wanted to make this equation 0. So that means either this term is 0 or this term is 0.
The first, yeah, or the second term, yeah.
So 10 minus 2x equal 0. Then x has to be 5.
5.
Which doesn't make sense because in this constraint up here, we said that x need to be less than 5.
Less than 5.
So
that's correct. It's not acceptable. The answer is not acceptable.
Not acceptable. And then the other equation is 10 minus 6x equals 0. That means x has to be 10 divided by 6 or 5/3. And this is, I think, the correct answer. So the size of the cut should be 5/3, and the unit is centimeter, 5/3 of the centimeter.
That's correct.
And then
we just need to, I think you need to add a page,
yeah.
Then we need to add, to substitute this value to the volume relation.
Right. So fx this one. So if
the volume the volume is x, yeah.
Right. So I'm going to write it down again here. X times 10 minus 2x is squared.
Yeah.
So 5/3 times 10 minus 2 times 5/3 squared. Let me calculate this.
I can help it.
Oh, okay. You have a calculator?
Yeah. Minus 10. Okay, the answer is 74.07.
0.07, and the unit is cubic centimeter because the units from the beginning.
That's the volume,
Right. So the volume of this box is, the maximum volume of this box actually is 74, roughly 74 cubic centimeter.
Yes. So if we have a cardboard and we want to make a box out of it, and we want to put more stuff in it, we can just look at the solution of this problem, and based on the initial size of the cardboard, the sheet that we have, then we obtain the volume of the open box, which is maximized. That's an interesting, problem in real life, so we can use it. Thank you, Hossein,
that's the
for
best way
helping
actually
me.
you can use the material.
Yes, with using less material you can actually have more volume. So appreciate it, and
No problem.
if you guys like the problem, please subscribe and hit the notification bell. I hope that you enjoyed the video today, and until the next video and next problem, have a great day. Thank you, Hossein.
Thank you. Bye everyone.
Bye.